Hello, today we're going to have a look at the vector equation of a line. So suppose we scattered a scalar multiples of, say, a vector b along a Cartesian plane, and we'd get something of the following. So we've got b here, and then that's b there, but this is 2b, and then 3b, b, minus 2b. Now if we were to plot all of the tips of these scalar multiples together, we would get a straight line through the origin parallel to b. Now if we let lambda represent any scalar, we could say that this new line, we don't know how long it is, but we could say it's lambda times b, where r is the position vector, and where r is the position of vector lambda b. So this would be the equation r is equal to 3b. This would be r is equal to minus 3b, which means any line, no matter the length, could be expressed as some lambda, some constant, times b. So if we were to plot all of the values of lambda along the line, we would see that obviously it would form a straight line. So we could think of the line r is equal to lambda b as the number parallel to b with distance given being integer multiples of b. So that's telling us that the gradient of b determines the gradient of the line. But no, we could move the starting point of this line at any point from the origin. We just choose a vector from the origin and add something onto it. So by tradition we state it and first add the scalar multiple of the second onto it, so the position vector starting is a. So we're adding some vector on to this vector line. So let's say we added on a. So the line r is equal to a plus lambda b is some vector a, and then we're adding on that straight line. So a tells us where the 0 point is, where our vector starts, and lambda b sets the gradient and how far apart these integers will be on the number line. So a vector equation is like a point gradient form of a line. Now it's important to realise that lambda is a parameter, which each value of lambda represents a single point of the line. So lambda is kind of like our x in the equation, y equals mx plus b, and b is kind of like our gradient. Now there is no unique vector form of a line, just like we can have more than one parametric form of a line making a Cartesian equation. So we could start the moving point represented by a to any point on the line, and we want to use a vector parallel to that line. So we can set two different vector equations for the same line. So this vector equation starts up here at point A and goes along B. So A, B, and that just tells us that it's this line here. Or we could go this way and start here and go downwards. This would still be the same line. So we can have many different equations which represent the same vector line. We can replace b with any vector parallel to it, so any vector having components in the same ratio. So for example, the following vector equations are all the same. And we can see because all of these numbers are either the same, a multiple of those, or it's going in the opposite direction, and it really just means the same thing, and we're talking about the whole line. So lines in 3 dimensions, so we've just been looking at 2 dimensions, lines in 3 dimensions look the exact same, except we have a third coordinate. It's just harder to draw them. So our first example we've got for the straight line with vector equation r is equal to a plus lambda b, where a is ijk and b is I minus j. Find the coordinates of the points for which, first of all, lambda is equal to 0. So I've got the equation r is equal to 1, 1, 1 plus lambda 1 minus 1, 0. So that's the equation, the vector equation of my line with the actual vectors placed into it. So when lambda is equal to 0, it's nice and easy. The coordinate of the point is just going to be 1, 1, 1, because everything here goes away. Part B, when lambda equals 3, we're just going r is equal to 1, 1, 1 plus 3 lots of this point. And that would just give us 3 minus 2, 1. So all we've done is multiplied that second vector by 3. Now all of these points lie along the same line because we've got the same starting point and we're just adding different multiples of the same vector onto it. Part C, r is equal to 100, so it's just 1, 1, 1 plus 100 lots of 1 minus 1, 1. And if you do that, you should get 101 minus 99, 1. Part D, where lambda is minus 5. Again, it's just 1, 1, 1 plus, or we should say minus 5, lots of 1, oh, there should be a 0 there, 1 minus 1, 0. And if you do that, 1 minus 5 minus 4, you get 6 and 1. Okay, sketching vectors equations. Now again, when we're sketching these vector equations, it's important to realise that there are many different ways that we can represent the same vector. And there's also 2 methods of sketching the vectors, and you can decide which one you like best. So suppose we wish to sketch the vector r is a plus lambda b. So our second example today, so we're sketching r is 1, 2 plus lambda 3, 3. The first method is to draw position vector A. So 1, 2, let's go 1, 2, 3, 4, 5, 1, 2, 3, 4, minus 1, minus 2, minus 3. So 1, 2 is going to be right here. So that's our vector A. And then we're sketching minus 3, or 3 minus 3. So we're going across 3, 1, 2, 3, and down by 3. 1, 2, 3. So it's going to be over here. So that's 1, 2, 3, and down by 3. So that's my second vector there. Then we can go over that and draw the vector equation of the line. So that is my line there. Method number 2 is to draw position vector A and then draw position vector B if we set lambda to be 1 and draw a straight line between the points. And realistically, it's the same thing as what we've just done. So draw straight line that one and then draw that line there as we've set lambda to be 1, and then we just draw a straight line between the points. I personally prefer the first method, but either methods get you the same thing. Really, we're just drawing a straight line. Okay, sketching an interval. Again, sketching intervals in 3 dimensions is naturally going to be a bit harder because we're dealing with that z dimension, but it's a skill that we need to have. So we're sketching the interval r is 2, 3, 4 plus lambda 1, 2 minus 1 from lambda is 1 to 3. Now the first point of call with these questions is go, okay, hey, what are the endpoints of this interval? So let's set lambda to be 1. R is going to be 2, oh, I should stop saying R because that's not the vector equation of the line. We could just say x, y, z because we're finding a point, is 2, 3, 4 plus lambda 1, 2 minus 1. Let's set lambda to be 1. So replace this with 1, and if I do that, I get 3, 5, 3. If we do that same for let lambda be 3, x, y, z is equal to 2 plus 3 is 5, 9, 1. So we're going to graph the 2 points 3, 5, 3 and 5, 9, 1, and we're going to sketch the interval between those points. So let's draw our Cartesian plane, x, y, z. Let's do 3, 5, 3. We might go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Or we have to go to 9. I might make the y's a bit smaller. Let's go to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3, 5, 3, 3, 5, and we're going up to 3. 3, 1, 2, 3, 4, 5, 1, 2, 3. There we go. 3, 5, 3, and then 5, 9, 1. 5, 9, 1. There we go. So that's 3, 5, 3, and 5, 9, 1. And it's probably best if we go like this. So that's 1. That's 5, 3, 3. Might move that a bit. And then this is, so 3, 5, 3, and then we've got 5, 9, 1. Okay. Finding a vector equation of a line between 2 points. So to find the equation of a line between 2 points, say A and B, we first of all need to find vector AB and then rewrite the equation as OA plus lambda AB. So lambda AB is the vector between the 2 points, and OA is that starting point of the line. So it starts at A and then goes off to AB. So remember, in extension 2 vectors, OA, and this is what I'm just saying, OA represents where the vector sits on the plane, kind of like the y-intercept, however it's not necessarily a line on the y-axis. AB represents the gradient of a line, but it's in vector form, and lambda is symbolic of x as in a normal equation of a line. Now, since B could represent any point of the line, then AB could have an infinite number of possibilities. Therefore, there are an infinite number of equations that could represent the same vector. Now, any vector equation in the form R is A plus lambda B, with A and B, whose vectors are any multiple of each other, are coincident. So if you've got A and B that are vectors that are multiples of each other, sorry, I should rephrase that. If you've got two vectors with the same A, and then you've got B, and B, in the two vectors, the B has one is multiple of the other, then they're coincident, they're the same equations. So same kind of y-intercept and same gradient or multiple of the same, then it's the same line. Any vector in the form R is A plus lambda B, whose B vectors are any multiples of each other, are parallel. So that's saying if B is a multiple in each of them, they're multiples of each other, but A is not necessarily the same, then they're parallel. And any vector whose B parts are a dot product to give 0 are perpendicular. So example 4 in today's lesson is find the vector equation through the line 2, 3, and 5, 7. Okay, all we have to do, this is very, very easy, this question. It starts at 2, 3, so R is equal to 2, 3, plus lambda, and we just got to find the vector between those 2 points. So 5 minus 2 is 3, and 7 minus 3 is 4. So that's one correct answer. You could, actually no, that's the only answer to that form, but if it said find a vector equation, actually no, I reckon there are multiple correct answers to this question, because if you made this 6, 8, it's still a vector that goes through that line there. So I would say there's multiple correct answers, but just do the easiest one there. Part B, find the vector equation for the interval 2, 3 plus 5, 7. Didn't we just do that one? Find a vector equation for the interval. Oh, okay. vector equation, this is an interval. So let's just do first of all the whole equation. R of t is equal to 2, 3 plus, what did we say, 3, 4. Now this is an interval, so it starts at 2, 3, and we've got lambda, and then we're going to 5, 7. So if lambda was 0, then it would be at 2, 3, and if lambda is 1, then it would be at 5, 7. So if lambda was less than 0, then it's going back before the interval starts, and if lambda is greater than 1, then it's going after 5, 7. So therefore, that's the equation there, and lambda is between 0 and 1. So that would be our interval there. Part B, we've got to prove that these lines are parallel. So we've got R is 3 minus 2 plus lambda 2 minus 4, and Q is 4, 1 plus lambda minus 1, 2. Now parallel lines, this component has to be a multiple of the other one. Whoop. So first of all, we know that, well, let's go, we've got 2 minus 4. Well, that has to be minus 2 lots of minus 1, 2. And yeah, if we multiply it through, then it's true, so therefore they're parallel. Prove that these lines are perpendicular. Well, perpendicular vector equations of lines are perpendicular when the dot product of this part is 0. So let's find 2, 3, minus 1, dot product, minus 1, 1, 1. Well, that's going to be minus 2 plus 3 minus 1, which is 0. So therefore, R is perpendicular to Q. Part 8, find the vector equation to the straight line joining the points 5, minus 2, 6 and minus 3, 4, 1, and find the coordinates of the point on AB where lambda is 2. So first of all, the equation, let's just call it R is equal to, and I keep saying, I think I've been doing R of t. Yep, that's wrong there. We're just saying R. So for this lesson, if I've got R of t, it's just R because we're not parameterizing anything. So R is equal to, we've got, starting at A, 5, 2, 6, plus lambda, outside of, minus 3 minus 5 is minus 8, 2, minus 5. So that's the vector equation of the line, and we've got to find the coordinates of the point on AB where lambda is 2. So x, y, z is equal to 5, 2, 6 plus 2 minus 8, 2 minus 10. So we've got 5 minus 16, which is minus 11. And then 2 plus 4 is 6. And then 6 minus 20, well, what's that? What number is that? Minus that should be a minus 5 there. 6 minus 10 is minus 4. So the answer is minus 11, 6 minus 4. Okay. Next example is find the vector and parametric equations of the line. First of all, in part A, the point A is minus 2, 1, 4. Parallel to the vector B is 2, 1, minus 2. Okay. Now, if we call the tip of the vector B and then found in the equation of the line between A and B, then this would not be parallel to B. So if we call the tip of vector B and then found the equation of A and B, then this would not be parallel. I'm not going to draw a diagram to represent that. I might just have a go at the question. So the vector point through A parallel to that vector. I feel like I'm overcomplicating it with that there. So let's just say R of t it's simply just going to be minus 2, 1, 4 plus lambda lots of 2, 1, minus 2. So it's going through this point and it's parallel to that. So all we're doing is going to that point and then drawing a vector that's parallel to B, which is just the vector B itself. And the important thing about that is vector B, we can move it anywhere in the Cartesian plane, in the 3D plane, and it still means the same thing. This vector does not necessarily mean OB. So part B, we've got through the point, I might do it down, no, part B's here. Through the point 1, 3, 2, and parallel to that line there. So R is simply going to be, we're going through this point, plus lambda, we want a vector parallel to that. So let's go C minus B, 3 minus 1 is 2, 4 minus 2 is 2, and 1 minus 3 is minus 2. So we've just found the two Cartesian equations, or the vector equations, and now we need to find the parametric equations. So the parametric equation for part A is simply going to be x is 2 plus lambda 2, so x is minus 2 plus 2 lambda. Y is equal to 1 plus lambda, and z is equal to 4 minus 2 lambda. Part B, x is equal to 1 plus 2 lambda, y is equal to 3 plus 2 lambda, and z is equal to 2 minus 2 lambda. Okay. Last couple of examples for this video. Question 10, so we've got given point 1 is 1, 2, 2, 1, 2, point 2 is minus 1, 3, 3, with P1 is a fixed point. Find the vector of equation of L that passes through P1 and P2. And we're doing a vector equation. So what we might do is, let's call it we'll call it line L. Vector line L is simply going to be, and P1 is a fixed point. So let's just start here, 2, 1, 2. And we want a point that goes through those. So L is equal to, so we've got P1 is 2, 1, 2, and P2 is minus 1, 3, 3. So what we might do is find P1 minus P2. So P1 minus P2. Oh, actually, let's do P2 minus P1 because our fixed point is P1. So P2 minus P1 is going to be minus 1 minus 2, which is minus 3. And then 3 minus 1, which is 2. And then 3 minus 2, which is 1. So the equation of my line, and we've got the vector equation of my line, is simply going to be R is equal to the fixed point 2, 1, 2 plus lambda lots of, if we're going through this point, well, lambda is equal to 1, then we're going through this point first of all, minus 3, 2, 1. So if we set lambda to be 1, 2 minus 3 is minus 1, 1 plus 2 is 3, and 2 plus 1 is 3. So if lambda is 1, yet we're going through that point, and then whatever we set lambda to, that's the equation there. Now, some people, you can express this vector line in a separate form. So you can parameterize if you'd like. So you can say this is 2 minus 3 lambda I. So this is really putting in its parametric form, but putting in a Cartesian format. And then we've got 1 plus 2 lambda j plus 2 plus lambda k. And those two things mean the exact same thing. So part B says the parametric equation. Well, we're just going x is 2 minus 3 lambda, y is equal to 1 plus 2 lambda, and z is equal to 2 plus lambda. So the advantage of leaving it in this form is we can directly see the parametric equation of the line. Part C, now P2 is a fixed point, and we're going to do the same thing, except P2 is now our starting point. So the line R is, the P2 is our starting point, so we're going from minus 1, 3, 3. And we're plussing some type of lambda, and we want to figure out what vector is going to get me from P2 to P1. So really this time we're going P1 minus P2. Let's do that over here, P1 minus P2. Well, that's just going to be 2 minus 1 is 3. And then we've got 1 minus 3 is minus 2. Is it 1 minus 3 is minus 2? And then we've got 2 minus 3 is minus 1. So 3 minus 2, 1. Note that this is the exact same thing as this one, except we're going in the opposite direction now. So therefore R is going to equal minus 1, 3, 3 plus lambda, lots of 3 minus 2 minus 1. Let's check if that works. So let's check if we start at P2, minus 1, let's set lambda to be 1. So minus 1 plus 3 is 2, yet we do arrive at P1. 3 minus 2 is 3 minus 2 is 1, we do arrive at P1. And 3 minus 1 is 2. Good. So that's my equation there. Part D, find the vector equation. X is going to equal minus 1 plus 3 lambda. Y is going to equal 3 minus 2 lambda. And Z is going to be 3 minus lambda. Okay. Last example for today, find the vector equation and Cartesian equation of the line through the point 2 minus 1 parallel to that vector. Okay. Vector equation, nice and easy. So R is simply going to be, we're starting at 2 minus 1, and we're just adding this vector that we're parallel to, 1, 2. So that's our vector equation there. Let's find the Cartesian equation. To find the Cartesian equation, we parameterize. So x is 2 plus lambda, and y is minus 1 plus 2 lambda. And we just need to solve. So from here, lambda is equal to x minus 2. If we put that in, we're going to get y is equal to minus 1 plus 2 lots of x minus 2, which will give us y is equal to 2x minus 5. Okay, thanks for listening. That's what did we do today? Parameterizing equations in 3 dimensions. Thank you, and lines in 3 dimensions.